Good morning, everybody. Today, I'd like to finish off my series on projectile motion problems by finishing up this particular challenge problem. There's not a whole lot of information provided in the problem description. It's really just 3 sentences, but we're told that it's especially difficult compared to the ones that we've done previously, and that it also requires calculus. So let's see how this one pans out. We are told that there is a projectile that is thrown from a point P. To make things simple, let's go ahead and put point P right at the origin of a two-dimensional coordinate system. We'll have plus x in this direction and plus y in this direction, like you're probably familiar with. And the second sentence says that the projectile moves in such a way that its distance from P is always increasing. Distance from P, or if you want to think about it in terms of the drawing, the projectile's distance from the origin is always increasing. So if I drew the projectile at one moment in time, for example, let me make that a little bit more straight. The distance between point P and the projectile is this, and we'll call it r. Let's recall a familiar formula from, I'd say, pre-calculus. We know that the distance between 2 points in 2 dimensions is given by the square root of x squared plus y squared. You probably know this from the Pythagorean theorem. Same thing. Now, in this second sentence, we're told the projectile is moving in such a way that its distance from the origin is always increasing. So that means that the distance between the projectile and the distance between the origin, that rate of change is positive. It's always positive. It's always increasing. Okay? So when it comes to rate of change, that typically means that we're taking a derivative. And since this projectile is moving around in time, it means we'll be taking a derivative with respect to time. So if we were to take a derivative of both sides of this expression, we would get the derivative of the distance between the point P at the origin and the projectile with respect to time is equal to d over dt of all of this. However, there's no explicit t expression here for x and y, so we need to rethink about what kind of expression we have inside of this derivative. And if we recall the formulas for x and y from the previous videos that I have done, remember that x is equal to the initial velocity times the cosine of the angle involved multiplied by time. And for y, typically we would say that there's like an initial y. We'll say like y initial plus v initial times the sine of theta times t minus 1/2 gt squared. But we can simplify this one a little bit because we said that P was put at the origin to keep things simple. And that means that the initial y value is just going to be 0. So honestly, we could just ignore this piece altogether and just say that y is equal to initial velocity times sine theta times t minus 1/2 gt squared. And these expressions for x and y, x and y, that's what we're plugging in underneath here so we can apply the time derivative. And what exactly does that look like? Well, dr dt is equal to d over dt of the square root of a whole bunch of stuff. So the radical is going to be really large. Initial velocity times cosine of theta times t. This is the quantity that's squared for x. Okay? And then we need to add v initial times sine of theta times t, and subtracting 1/2 gt squared. And that quantity is squared. Okay? So that is what we are essentially taking a derivative of. But to take the derivative now would be to kind of jump the gun a little bit, because we need to do some simplification. And in fact, the piece right here can be simplified to look a little bit nicer. So let's go ahead and do that off to the side. I'm going to write this out like this so we can kind of see the foiling in action. Here, that might be a little high. Let's try this. Move this over. Nope, that's still troublesome. So let me write it out. Pardon me on that. V initial times sine theta times t minus 1/2 gt squared. And if you're not super familiar or comfortable with the idea of foiling a quantity, especially when it's variables like this and not numbers, I recommend kind of like color coding things. I'm going to make this red and blue, and then we'll call this orange and green. Okay? So for the first FOIL, we're taking red times orange, which is what? Well, reddish orange is V, that's a little bright, V initial squared times sine squared of theta times t squared. Okay? So that was red and orange being multiplied together. If I do red and green, I don't know if I can represent that nicely here on the screen. So let me maybe just do that in red. We're going to take minus 1/2 times g times v initial times sine of theta times t cubed. Okay? Why t cubed? Well, we've got a t here, and we're multiplying red and green together in the FOIL, and there's a t squared over here too, so we can't forget about that. And in fact, we'll end up getting a second quantity of exactly the same thing, minus 1/2 times g times v initial times sine of theta times t cubed. And then for the final piece, we're taking the blue underlined quantity here multiplied by the green underlined quantity, and perhaps I'll report that in purple, which is, that's pretty easy. That's just 1/4 g squared t to the 4th. So that, everything over here is what y squared is. So let's maybe incorporate all of that, just so we can kind of see how the chips are kind of falling together. So I'll rewrite this pretty long. I'll say that we have v squared cosine squared of theta times t squared. We also have plus v initial squared sine squared theta times t. minus a half of everything in red over here, minus a half of the same thing. Well, negative a half minus another half is like negative of just that quantity, so we'll end up with minus g times the initial velocity times sine of theta times t cubed, and then we add on that remaining portion in purple plus 1/4 g squared t to the 4th. And if you pay close attention to what's inside of the radical there, we have something very important. We have this quantity here and this quantity here. Oh, I actually forgot a squared on the t. Forgive me there. They both have t squared in this quantity. They both have v initial squared, but they have cosine squared plus sine squared. There's a very, very important identity, which I'm sure you may remember. Cosine squared of whatever angle plus sine squared of whatever angle, well, that's just equal to 1. So what we could do is we could just factor out v initial squared and t squared and get rid of this cosine squared plus sine squared. What would that look like? Well, the derivative of the distance from point P to the projectile with respect to time is equal to the derivative with respect to time of square root v initial squared times time squared, right? We got rid of the cosine squared and the sine squared by adding them together, and we said that was 1. And we factored out v initial squared and t squared, so that's where this is ending up from. And we still have minus g times v initial times sine of theta times t cubed plus 1/4 g squared t to the 4th. Get rid of this excess radical here. And that, ladies and gentlemen, is what we need to take a derivative of. We're finally at the point where we can do the derivative. We had to do all this simplification just to get to this point. And now here we encounter another roadblock, because the question is, well, how do I take a derivative of this? Like, wow, that looks nightmarish. Well, it's actually not too bad. And in fact, if you are familiar with U substitution, it will come across as probably a pretty easy exercise. So if I go to a fresh page, I'm going to look at the expression that I want to take a derivative of, and I want to look at the most innermost function. Okay, the outermost kind of function is a square root sign. The innermost is everything that's contained inside that square root, so everything that I'm kind of underlying in purple. So I'm going to let u, in my U substitution technique here, be equal to everything I had underlined in purple. V initial squared times t squared minus g times v initial times sine theta times t cubed plus 1/4 g squared t to the 4th. Okay? That is what we are letting u equal. What's the next step in u substitution after you have found what u is? Well, we take a derivative of u with respect to the variable that we're trying to do the overall derivative of, and that would be time. So that would mean we want to do du dt. What is that? Well, that's d over dt of everything that I just wrote up here in purple. V initial squared times t squared minus g v initial times sine of theta times t cubed plus 1/4 g squared t to the 4th. What does that turn out to be? It's actually a pretty simple derivative and application of the power rule. We end up with, I get 2 times the initial velocity squared times time minus 3 times g times the initial velocity times sine of theta multiplied by t squared. And then for the last piece, the 4 will come down, it will completely eliminate the coefficient, and we end up with g squared t to the third. And that's what our derivative of u with respect to t is. Now let's finish off the u substitution method. We are taking ultimately a derivative with respect to u of the square root of u and then multiplying that by du over dt. That is the entire approach of the u substitution method. And in fact, to make this a little easier, instead of writing the square root of u, let's rewrite this in exponential notation, because then it makes it abundantly clear what needs to happen. Okay, so we're taking the derivative of u to the 1/2 power and then multiplying it by all this stuff that we just took a derivative with respect to time to. And what does that turn out to be? Well, we end up with 1/2 multiplied by 1 over u to the 1/2, okay, multiplied by 2 times the initial squared times t minus 3g v initial sine theta t squared plus g squared t cubed. And remember, what is u? Well, we had u be equal to everything in purple up here. However, if we go back to the first page, we said that r is the square root of x squared plus y squared. And that's basically the square root of everything here in purple. So I'm going to do something here that is going to require a little bit less writing than writing everything out. I'm going to multiply 1/2 by 1 over r. Why is it r? Remember, the square root of everything in purple here is equal to r. And if we have everything in purple set as u, and we're taking the square root of u, that's the same thing as r. Okay? And then we also have to include the stuff at the end where it's 2 times the initial squared times t minus 3g the initial times sine of theta times t squared plus g squared t cubed. And remember, this is still equal to the derivative of the distance between point P and the projectile with respect to time. So the derivative is done. This is actually what it is, but the question did not ask us to find the derivative of this expression. If we go back to the first page, it says that the distance from P is always increasing. The distance from P is always increasing. The rate of change from the point P to the projectile is always increasing. How can we mathematically show that? Well, that means that it has to be greater than 0. It has to be greater than 0. It can't be greater than or equal to 0, because that would mean it would be increasing or remaining the same. It has to be specifically greater than 0. And what's cool about it being greater than 0 is we can do some algebraic manipulation and just get rid of this 1 over 2r. In fact, let me start up another fresh page here, and I will go back to this piece. the very last line that we solved on. And if I have this as my expression, 1 over 2r 2v initial squared times t minus 3g v initial times sine theta is t squared plus g squared t to the third, and this is greater than 0. What's cool is I can multiply both sides by 2r, and 0 times 2r is just 0. So that's pretty sweet. 2 v initial squared times t minus 3g v initial times sine theta multiplied by t squared plus g squared t to the third is greater than 0. So that's what we have. And we can go even further, right? There's a t variable in every single chunk of this expression. T here, t squared here, t to the cubed here. Let's divide both sides by t, which does what? Well, we'll get rid of it here, we'll get rid of it here, and we'll get rid of that and turn that into the 2. So we get 2v initial squared minus 3g v initial sine theta multiplied by t plus g squared times t squared greater than 0. So that's kind of cool, eliminating the t's on both sides and eliminating the 1 over 2r piece from up here turned this expression into a quadratic in t. In fact, if I label a, b, and c in the same way that I've been doing for the previous problems, here's our a, the g squared. The b is this minus 3g v initial sine theta. And then for c, it's just this 2 v initial squared. And what are we doing? Let's kind of remind ourselves why we're even trying to use the quadratic formula. What is happening here? We're taking the derivative of the distance between point P and the projectile, and we're told it has to be always increasing. So that means we need to solve for a time that's specifically positive and real that allows those conditions to be true. So that means when we're using the quadratic formula on this a, b, and c, like always, we need to get a time that's positive. We can't get like a time that's negative. That doesn't make sense here. So remember, t is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And this is actually a situation in which I will write out everything here because there's something a little important going on here. So the negative of b is going to turn this negative 3 into a positive 3. So we'll have 3g v initial sine theta plus or minus the square root of b squared, so we'll say negative 3g v initial sine theta, and that is squared minus 4 times a, which was what? G squared. C is 2 v initial squared. And this is all over 2 times g squared. So our goal was to solve this quadratic expression and try to find time, or a time, or a solution to this quadratic formula that's positive, right? It's real and it's positive. If I look at some of these quantities here, 3 is a positive number, g is just 9.8, It's not actually negative 9.8 because there's no negative in front of it. It's just regular 9.8. The initial velocity is going to be a positive number, and the sine of an angle between 0 and 90 degrees, theta is equal to 0 degrees, and then theta is equal to 90 degrees. There is always a positive value for sine, right? Furthermore, in the denominator, 9.8 squared multiplied by 2 is also positive. So I can almost kind of like circle these quantities and say, this is always positive, this is always positive. Well, the real thing that we need to figure out is, what about the discriminant? Is the discriminant positive? Because if it is, that's a problem. We need our situation to have the projectile always increasing. And if you take a positive number and you subtract a positive number from it, it can't always be increasing. That's not possible. The only way that you can take a positive number and subtract another value off of it and make it continually increase is this discriminant has to be less than or equal to 0. It has to be. It has to be less than or equal to 0. If it's not, then there's no way that it can be continually increasing, right? Because that would mean that you might potentially get a negative time for this quadratic expression, which would mean that the distance is not always increasing in the way that we want it, right? It might be increasing in like quadrant 2 with a negative time, and that doesn't make any physical sense. So our discriminant here, the part that I have circled in this kind of brownish color, that is the part that we need to focus on specifically. We don't care about anything else. This discriminant has to be less than or equal to 0 to make all the work that we've done up until this point valid. So if I open yet another fresh paint slide here, and I rewrite the discriminant that we had, which was the square root of, if I go back, minus 3g initial velocity, and I think we said it was sine, sine theta, and this is squared, and this is subtracting 4 times g squared times 2, or pardon me, 2 initial velocity squared. And we said this discriminant, this part that we're focusing on specifically, has to be less than or equal to 0. So if we say that this piece here is less than or equal to 0, now we can finally get to an angle and solve the whole problem. Because what was the problem even asking for? In the first slide, it said find the maximum angle. Find the maximum angle above the horizontal with which this projectile could have been thrown. We're going to have multiple angles, but we need to find the largest one. So from this expression here, let's solve for theta. We'll square both sides, which leaves us with what's left here, sine theta squared, minus, if I take 4 times 2, that gives me 8. I get g squared v initial squared is less than or equal to 0. I can square this quantity, which gives me 9 g squared v initial squared sine squared theta minus this piece here, v initial squared is less than or equal to 0. Let's move this piece here to the other side and make it positive. So we have 9g squared v initial squared sine squared theta is less than or equal to 8g squared, the initial squared. Okay, we're starting to get somewhere. We've got g squareds on both sides and initial velocity squared on both sides. Let's get rid of them. We don't need that crap. Goodbye, goodbye, goodbye. Farewell. So 9 sine squared theta is less than or equal to 8. Okay, we're not in danger yet. We can keep going. We end up with sine squared theta is less than or equal to 8 over 9. And if I take the square root of both sides, well, it says that sine of theta has to be less than or equal to the square root of 8 over 9. And if I use an inverse sine argument, right, sine inverse of sine of theta, okay, is less than or equal to sine inverse of root 8 over 9. Okay, and I don't want to open up a new sheet, so let's maybe go off to the side here. This tells us that theta is equal to, or pardon me, not equal to, less than or equal to the sine inverse of the square root of 8 over 9. What is that value? Well, when you plug that into your calculator and you have it converted to degrees, it says that theta is less than or equal to basically 70.5 degrees. Okay, and this is reporting things to the appropriate number of significant figures. Well, I guess they didn't really give us any significant figures. Right? There's nothing provided in the problem description. So instead of saying 70.5 blah 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 blah, I just report it to 3. 70.5 degrees. That seems like a reasonable answer. So this is the largest of the angles possible to make this happen, right? So it's actually the answer is let's see, 0, 70.5 degrees, right? So theta can be all of these angles, any angle within that particular group, but we were asked specifically find the maximum one. Oh, well, that's pretty simple. If it can lie anywhere between 0 degrees and 70.5 degrees, well, then the maximum angle is 70.5 degrees. That's it. So max angle is 70.5 degrees. Okay? And that is the maximum angle at which you could throw this object from point P such that the distance from point P to the projectile will always be increasing. And that is the end of this challenge problem. Thanks for watching.